Here I'd like to do some integration using the substitution rule. These are just random problems I got from an old textbook. Now when you do these integration problems, you have to perform some sort of substitution to put the integration or the integrand in a more solvable form. And these techniques vary from problem to problem, but the more you practice, the more intuitive they become. So sometimes you can just look at the problem and already have an idea. Integration is often seen as the inverse of differentiation. So just for example, if we do something like, if we know that the derivative of sine x with respect to x is equal to cosine x, then the integral of cosine x dx is equal to sine x plus some constant. We normally just use c to specify that it's a constant. And in most cases, in these simple cases, I mean, it's normally quite trivial. And also in a case like when you have an integral of a polynomial of, let's say, x to the power n, dx, sorry, let me put the dx there. This is equal to x to the power n plus 1. So it's the inverse of differentiation. So we increase the power. With differentiation, we lower the power. But this is true for n not equal to negative 1. When n is negative 1, then this is the natural logarithm, which is ln x. This is also can be written as log. Some textbooks it will be log. Sometimes it will be log to the base e, just to specify that it's the it's Euler's number. That e is Euler's number, pronounced Euler. And this is for when n is equal to negative 1. Because obviously, if n is negative 1, you can't divide by negative 1 plus 1. So those are the general rules, but of course there are many more, and in some cases you'll be expected to, I don't know, memorize these rules. I don't know. Is it wise to memorize them? It's probably good for your memory, but most of the time you'll be given a table or a reference sheet or something, and you can always refer back to it. But I mean, like I say, if you practice regularly, you will start getting the hang of it. So let's solve the first one. So it's the integral of the square root of 2x plus 3 dx. So what we're going to do is we're going to do a substitution here. So what I'll do is I'll say let u equal to 2x plus 3. Then, now what we're going to do is we're going to take the derivative of u with respect to x. So we'll say then du is equal to, now what's the derivative of 2x plus 3? Well, with respect to x, so 2x, the derivative will just be 2. Plus 3, well 3 is a constant, so the derivative is 0. So it's just 2 dx. If there's a bit of confusion why it's like this, it would be, think of it like this: if you got du dx is equal to d dx of 2x plus 3, which is equal to 2. And then if you multiply both sides by dx, you have du is equal to 2 dx. So that's the reasoning behind this. And then if we want to make dx the subject of the formula, we can say dx is a half du. Now why are we doing this? Well, the thing is, the reason we do this is because now our integral, I'll rewrite the integral here, the integral of the square root of 2x plus 3 dx, what happens now is that the 2x plus 3 is now a u, and the dx is a half du. So our integral now becomes the integral of the square root of u times a half du. Now the half is just a constant, so it can be pulled out of the integral, sorry. So what happens is we get a half integral, and then the square root is it means it's the power of a half. So now you have u to the power of a half du. And then using the basic rule of integration, this becomes a half times, now when we integrate, we raise the power by 1, so it's a half plus 1, and divided by a half plus 1. And then of course we'll just remember to keep putting that plus c there. We don't care what c is. And then let's continue. So a half plus 1 is 3/2, it's 1.5. So we keep that half there. It's u to the power 3/2. And then this is all over 3/2. And then, okay, I'll keep the plus c, I mustn't forget. And then of course further simplification, we get a half times, so if we're dividing by 3/2, this becomes 2/3 times u to the 3/2 plus c. This is just algebra, it's just basic stuff. 2's here cancel, we end up with a third u to the power 3/2 plus c. And then let's substitute back. So we know what we made u was 2x plus 3, so this just becomes a third 2x plus 3 to the power 3/2 plus c. Now let's check if our answer is right. Now how do we check? Well, if indefinite integration is the inverse of differentiation, let's differentiate this and see if we get back what we started with. So let's do a d dx, and then let's put this thing in a third times 2x plus 3 to the power 3/2. I'll leave the c out because if you differentiate a constant, it's just 0. So it's just going to waste our time to put the c in. And let's see what we get here. So a constant, we just put it out there, it's a third. And then remember, with differentiation, we bring the exponent down. So 3/2. We keep the inner function the same, but we lower its power. So we lower it, it's 3/2 minus 1, we lower it, so it becomes half. And then we multiply, because we're doing the chain rule, we multiply by the derivative of the inner function. So the derivative of the inner function is just 2, because it's a derivative of 2x plus 3. And if we do this carefully, we'll see that the 3's cancel here. And then this 2 cancels with that half. And in the end, we're left with 2x plus 3 to the power half. And if we want it to look the way it looked in the beginning, that's just the square root of 2x plus 3. And this is what was inside our integral. So I dare say we are right. So we should be quite happy. And now for number 2, a little bit more complicated now. So now we're taking the integral of sine theta d theta all over the square root of 1 plus cosine theta. Let's draw that square root nicely. So again, we're going to use substitution, but now we need to be a little bit more creative, maybe. Maybe not, let's see. So I'll say let u equal, and we're going to see a nice trick here. So let u equal 1 plus cosine theta. Then du is equal to, so the derivative of 1 is just 0, so we ignore it. And then the derivative of cosine theta is negative sine theta. And then d theta, don't forget this. So this guy here, nicely corresponds to the numerator over here. So this is going to be good. This is going to make life a little bit easier. So our integral becomes sine theta, well, not becomes, I'm starting it from the beginning again, square root of 1 plus cosine theta. And now if we put in these substitutions, we're going to end up with negative, let's just put the integral sign first, negative du over the square root of u. And if we want to write it more decently, we put the negative outside, and we can write u as u to the power negative half, because it's in the denominator, and du. And then it's just a simple rule of integration, so what happens is it becomes negative u to the power negative half plus 1 all over negative half plus 1. And then we plus c as usual, just the constant. And a little bit of simplification here, a negative half plus 1 is a half. So we end up here with negative u to the power half all over half plus c. Further simplification, this just becomes negative 2 square root of u. Remember, power half is just the square root. And then we substitute back. So we remember what u was. What was u? U was 1 plus, u was equal to 1 plus cosine theta. So let's just remember that. That was the substitution we made. So our answer is negative 2 square root 1 plus cosine theta plus c. Now again, let's check. So what we'll do is we'll do a full-blown derivative here, d theta of 2, well, okay, let me put it in bracket, of negative 2 times the square root of 1 plus cosine theta. And again, I'll leave the c out because it's just going to be 0. And let's do this derivative here. So this is negative 2. Now this is of course the power half, so we bring down the half. The inner function 1 plus cosine theta, the power must be reduced by 1, so half minus 1 is minus half. And then we must multiply it by the derivative of the inner function, so the derivative of 1 plus cosine theta. And the derivative of 1 plus cosine theta is negative sine theta. This is the chain rule. And if we simplify, the negative here cancels with the negative there. The 2 here cancels with the 2 with the half. And then what we're left with is 1 plus cosine theta to the minus a half times sine theta. And if you want to write it in the form it was originally, we can do sine theta over square root of 1 plus cosine theta. And once again, we should be happy because this corresponds to the original integral. Sorry, I keep saying integrand by mistake. The integrand is what is inside the integral. And yeah, so that looks good. It's always good to test your answer. Okay, now let's look at number 3. So let's see what we can do here. So this is the integral of sine squared 2x over 1 plus cosine 2x. And then don't forget the dx there. So before we start panicking, we can ask ourselves, is there a way to simplify this? So from trigonometry there's a famous identity, it's sine squared, I'll use 2x here, sine squared 2x plus cosine squared 2x is equal to 1. This is a very important and famous trigonometric identity. So what we can do here is we can write sine squared x or sine squared 2x. So sine squared of 2x as 1 minus cosine squared 2x. Now what we'll notice here is that 1 is also equal to 1 squared, because 1 times 1 is 1. So we can write this as 1 squared minus cosine squared of 2x. And this is the difference of two squares. And if you remember from high school, difference of two squares allows us to decompose it as this. We can write it as 1 minus cosine of 2x multiplied by 1 plus cosine of 2x. You can verify this by expanding this bracket, but you'll see that it is correct. Now if we take our numerator and write it in this form, our integral simplifies drastically. So let's see that. So what happens is integral of sine squared of 2x divided by 1 plus cosine of 2x dx is equal to the integral of 1 minus cosine 2x multiplied by 1 plus cosine 2x. The dx must fit here somewhere. I'll put it in front here. And then 1 plus cosine of 2x. Let's put this in brackets. And these guys over here cancel. And then you're just left with the integral of 1 minus cosine of 2x. We put it in brackets dx. And this is a much simpler problem to solve. In fact, this can be done without even substitution, but let's just do the substitution anyway. So what we can do here is we can expand this. So this becomes the integral of 1 dx minus the integral of cosine 2x dx. So the integral of a constant is just the variable, so this is just x. And then the integral of minus cosine 2x. Well, I mean, we should know immediately that this is when you integrate this term. Okay, let me not say that. Let me not do that. So the integral of a constant is just the variable itself, so this just becomes x, and then minus the integral of cosine 2x dx. Now what's the integral of cosine of 2x? Well, we can do substitution here, so let's just do it quickly. So let u equal 2x, and then in that case du is just 2 dx. And if you want to make dx the subject of the formula, then dx is a half du. So now what we have is it's equal to x, we keep the x there, minus the integral of cosine of u, and then times a half du. And the space here, let's just go, this will just be x minus the half gets pulled out, and the integral of cosine is just sine. The integral of cosine is just sine, And when we substitute back, remember we made u 2x, so therefore it's just equal to x minus a half sine 2x. And of course I forgot to put the plus c. We're supposed to put plus c everywhere here. Don't forget to do that because you can lose marks, I suppose. Yeah, I think it was just there, I forgot to put it. And then let's just double check and see if our answer is correct. So let's just check. So if we check, we're going to just do a derivative here. So we do d dx of x minus a half sine of 2x. And I'll leave out the plus c again. So d dx of x is just 1. And then d dx of minus half sine 2x is minus a half. Derivative of sine is cosine 2x. And then we must also take the derivative of the inner function, which is 2x. So the derivative of 2x is just 2. So the 2 and the half cancel. So we're left with 1 minus cosine 2x, which was the simplified form of our integral. So this answer is correct. So question 4, or exercise 4, looks a bit intimidating. It's the integral of t times e to the minus t squared dt. E is Euler's number. So we don't need to be too scared of this one. I would imagine the substitution we make here is just, let's rewrite this thing first. Let's write it like this. Let's write it as the integral of e to the minus t squared times t dt. I wanted the t and dt to be next to each other so you can see it more clearly. So what we do is we say let u equal t squared. Then du is 2t dt. Now that's why I wanted to do that. I wanted this dt and the t and dt to be next to each other like that. So what we can do is we can say, okay, then t dt is equal to a half du. Now let's do the substitution. It's so nice to see this substitution stuff in working out. So our integral of e to the minus t squared times t dt becomes the integral of e to the power minus u times, and then the t dt is just a half du. So I'm just move the half out of the integral, and then this is just du, and this is just the integral of the exponential Euler's number. So this is just a half times e to the minus u times minus 1, because the negative in the exponent falls down. So you end up with and let me not forget the plus c. This plus c is so annoying. So we have minus a half e to the minus u plus c. And when we substitute it back, it's just negative a half e to the minus t squared plus c. And I suppose we can test it quickly. So let's just check if this is correct. So let's check the derivative d dt of negative a half times e to the minus t squared is equal to what? Well, the negative half stays there. E obviously stays there to the minus t squared, but then we must take the derivative of minus t squared, which is minus 2t. So the minus 2 and the half cancel out, and we're ultimately left with e to the minus t squared times t, which is exactly what we originally, well, that's what our problem was from the beginning. So now we can go on to question 5. So question 5 is the integral of x dx over the square root of 1 minus 4x squared. So what are we going to do? What are we going to choose to substitute in here? So I think we'll probably just take the guy that's inside the square root. So let u equal 1 minus 4x squared. Then du is equal to negative 8x dx. So this x dx corresponds to the numerator, so that's what we like to see. And then if we just make that the subject of the formula, x dx is equal to negative 1 over 8 du. Now let's substitute that back into the original integral. So we've got x dx all over 1 minus 4x squared square rooted, and this is equal to negative 1 over 8 integral, and then the x dx was the negative 1 over 8, and then the du, and at the bottom we'll have square root of u. And this is quite a straightforward integral. We came across this one earlier, something very similar. So this is just negative 1 over 8 times u is a minus a half plus 1 over minus a half plus 1 plus c, and this is negative 1 over 8 times u to the power half over half plus c, and this is equal to negative a quarter, I'm just simplifying, square root of u plus c. And then when we substitute the u, what was substitute for u back in, we get negative a quarter times the square root of 1 minus 4x squared and plus c. And now we can check using differentiation, using the chain rule. Let's just check if this makes sense. So we do d dx of a quarter, negative a quarter, times the square root of 1 minus 4x squared. Once again, I'll leave the c out because it's just going to be 0. So we have a negative a quarter. Now remember, with differentiation, this power half, we bring down the half. The inner function gets reduced by 1. So the power of the inner function, I mean. So this becomes negative half. And then we multiply by the derivative of the inner function, which is negative 8x. And if we do a little bit of arithmetic here, we can see that the negatives will cancel. And then a quarter times half is an eighth, so the eighth and the quarter and the half disappear. And then we're left with 1 minus 4x squared to the power negative half times x. And if you want to write it the way it was originally, the x is on top and this guy is at the bottom. 1 minus 4x squared all under a square root. And this is what we were given in the beginning. So again, we can be happy. And I think let's just do one more. I think it's a bit long now. But anyway, let's do the integral of cosine squared x times sine x dx. So this is trigonometric again. We need to just see probably some manipulation involved here. What can we do? So we know that sine and cosine, the derivative of one is the other. So maybe we can make the substitution of, we can make u cosine so that the derivative will be sine x. That might work, so let's try that. So let's do this. Let u equal cosine x, then du is negative sine x dx. and then this is what will happen. So we'll have cosine squared x times sine x dx is equal to the integral. So cosine is u, so this becomes u squared, and then sine x dx, this guy here, is just du, well, negative du. So we can put the negative outside and then du. So the integral of u squared, well, negative u squared, and this will be negative u to the power 3 over 3 plus c. And if we plug in back what our substitution was, this is just negative cosine cubed of x over 3 plus c. And let's test it. So let's check. If we do d dx of negative a third cosine to the power 3 x, what do we get? Well, we get negative third, then we bring down the 3, and then we say cosine to the power 2, because we have to bring down the 2, the power, sorry, we have to bring down the power, so the power 3 becomes power 2. But don't forget, we need to also multiply by the inner function's derivative, which is cosine, so it will be negative sine x. Let me explain that a little bit more after I simplify here. So the 3 and the third cancel, and the negative there cancels with negative. So we end up with cosine squared x times sine x. So this is again 100% correct, but I just want to explain what I meant there when we did the derivative of cosine cubed. When you take the derivative of cosine cubed, what you're saying is it's the derivative of cosine of x to the power 3. So what happens is you bring the 3 down, you keep cosine as it is, you reduce its power by 1, so it becomes squared. But because of the chain rule, you also have to take the derivative of the inner function, and this guy now gives us a negative sine x. So I just wanted to make that a bit clear. But anyway, yeah, so we've done 6 problems. I think that's quite a lot, and we'll do more advanced techniques in a later video. Alright, thank you, bye bye.